Hello. This podcast is the first in a two-part series on describing uniformly accelerated motion. We'll learn what accelerated motion is, how we describe it with words, and motion maps. In part 2, we'll see how we describe it with position time and velocity time graphs. Let's take a look at what is accelerated motion. Well, it's the alternative to constant velocity. We said with constant velocity, the object is moving the same speed all the time. In other words, it covers the same distance every second. Well, accelerated motion, the velocity is changing. It's either speeding up or slowing down. And that's something we should talk about. In everyday language, we think of accelerated or accelerating as speeding up. But in physics, it means the velocity is changing. And that can change either increasing, which we call speeding up, or decreasing, which we call slowing down. Let's take a look at a couple examples. In this first example, it's a car pulling away from a traffic light when the light turns green. At time 0, their velocity is 0. 1 second later, their velocity is 2 meters per second, and 2 seconds later, their velocity is 4 meters per second. Clearly, we can see this is not constant velocity, so this is accelerated motion, and we would call this speeding up since the velocity is increasing as time goes on. Let's look at the opposite of speeding up. Here, we're approaching a traffic light, and it turns red. So we apply our brakes. At the time we saw the traffic light change red, we were traveling 10 meters per second. We applied our brakes. A second later, we were moving only 5 meters per second. And 2 seconds later, we came to a complete stop. So again, we can see this is not constant velocity. The velocity is changing, so it too is accelerated motion. Now, in physics, the official definition of acceleration is the rate at which an object's velocity changes. The term uniform acceleration applies to a specific or special case where the object is accelerating and the velocity changes at a uniform rate. Both of these examples here are uniform acceleration. For instance, in the case of pulling away from the traffic light when it turned green, in the first second, the car increased its velocity 2 meters per second. In the next second, it also increased its velocity 2 meters per second. So the rate at which the velocity was changing was constant, 2 meters a second every second. If we look at the slowing down example, coming to a stop at a red traffic light, the change in velocity was a decrease of 5 meters per second in the first second, and in the next second, it also decreased 5 meters per second. So this is a case of uniform acceleration because the rate at which the velocity changed was the same. It decreased 5 meters per second every second. Now let's take a look at an example of accelerated motion, and we're going to have a dune buggy here. And that's going to be our constant velocity motion, and the fan cart will notice the accelerated motion. So let's do that one more time. Notice that the fan cart is gaining speed while the dune buggy is maintaining a constant velocity. So if we go back to the beginning, and I'll just walk this through step by step, notice that the dune buggy is starting to go at a fast velocity compared to the fan cart. But as time goes on, the dune buggy maintains its constant velocity, and now the fan cart's going faster and faster, and it overtakes the dune buggy. Now let's look at some things here about this. Here I've placed dots. These are kind of hard to see, but if you look at the blue dots, this represents the motion every half second. So this is the position every half second at time equals 0, half a second, a second and a half, 2 seconds, 2.5 seconds. The red dots represent the position of the dune buggy every half second. 0 seconds, half second, 1 second, 1.5 seconds, 2 seconds. So if we look at the dune buggy's dots, we notice that they are equally spaced. That means every half second the dune buggy covers the same distance or has the same displacement for every half second. And that's the characteristic of constant velocity. Notice it's completely different with the fan cart. The displacement from time equals 0 to half a second is very small. When we go from half a second to 1 second, it gets larger. When we go from 1 second to 1.5 seconds, it gets even larger, and so on. As every half second increment goes by, the displacement gets larger, and that's the characteristic of an object that is speeding up. Let's take a look at some words we can use to describe this fan cart's motion. It's moving to the right, also known as the positive direction. It's speeding up. Its velocity increases as time goes on. Its displacement increases each second as time goes on. And we would say it's accelerating to the right or accelerating in the positive direction. Now, let's take a look at another type of motion. We have our dune buggy and our fan cart again, and let's watch this motion. Okay, let's watch it one more time. Notice, I'll just kind of go through step by step. At the beginning, the fan cart is going faster than the dune buggy. But as time goes on, the fan cart starts to slow down while the dune buggy maintains its constant velocity. And eventually, the dune buggy catches up to the fan cart because the fan cart comes to a stop. Now, let's take a look at these dots. Again, not surprisingly, the dune buggy's dots are equally spaced. That means that every half second, it's going the same distance as it did the previous half second. However, different story when we look at the blue dots representing the fan cart. Notice in the first half second, the displacement was relatively large, and in the next half second, the distance traveled or the displacement was smaller. In the third segment, this half second segment, it got even smaller, and the displacement got smaller in the next half second, and in the following half second it got smaller. And that's a characteristic of something that is slowing down. Every unit of time that goes by, let's say every second, the displacement gets less and less. Let's look at some words we can use to describe this fan cart's motion. It's moving rightward, or in the positive direction, just like the previous motion. However, this time it's slowing down. The velocity decreases as time goes on, and displacement decreases each second as time goes on. And in this case, the acceleration is in the left direction or negative direction, and we would say it's accelerating leftward or accelerating to the left. Let's take a look at the motion maps for speeding up and slowing down. First, we'll look at speeding up. And first thing you'll notice is that we have two sets of dots, and we've got a V up here and in lowercase a down here. The V stands for velocity, and so these arrows, they're vector arrows, they represent the velocity. The dots mean the same thing as they did in the last unit. They show the position at different times, starting with 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. The new part of the graph down here, or new part of the motion map down here, is showing the acceleration. So the position dots are in the same place as we've always drawn them, but now these arrows represent the acceleration. Okay, and we had said that the acceleration is going to the right. Now the acceleration happens to be constant, and we'll explain later on in a different podcast why the acceleration is constant. But let's go back up to the top. We know when something's speeding up, as each second goes by, the displacement gets larger. So that means the dots have to get further and further apart. So notice between 0 and 1 seconds, it was 1 unit. Between 1 second and 2 seconds, the displacement was 2 units. Between 2 seconds and 3 seconds, the displacement was 3 units. And between 3 seconds and 4 seconds, the displacement was 4 units. And our velocity arrows also have to get longer, because again, we'll draw the velocity arrows halfway between the dots. So both the velocity arrows getting longer and longer indicates the object is speeding up, as well as the fact that the spacing of the dots gets larger and larger as time goes on. Those two things indicate an object that's speeding up. Now let's look at slowing down. We can see our dot spacing initially is large, but as time goes on, the dot spacing gets smaller because the object is not covering as much distance each second. The velocity arrows are also getting smaller because the object is slowing down and not going as fast. With the acceleration, the dots are in the same place because the position of the cart is the same whether we're talking about velocity or acceleration. But now the acceleration is going to the left, so we need to show the arrows pointing to the left. And one characteristic of an object slowing down, the velocity arrows and the acceleration arrows will always point in the opposite direction. So in this case, the object was slowing down to the right, so the velocity arrows are pointing to the right, and the acceleration is pointing to the left. If the object was moving to the left, then the velocity arrows would be pointing to the left and the acceleration arrows would be pointing to the right. When an object is slowing down, the acceleration is always in the opposite direction of the velocity. Now, the opposite is true when an object is speeding up. When an object is speeding up, the velocity and acceleration are in the same direction. So an object speeding up to the right will have both its velocity arrows and acceleration arrows pointing to the right, and an object that's speeding up to the left will have its velocity arrows and acceleration arrows pointing to the left. This ends part 1 of our 2-part series on describing uniform acceleration. I hope this helped, and have a good day.